Good afternoon, everyone. Let's start with this session. It's going to be somewhat on contact, but actually slightly more than that. So let's talk about the idea of I've got a solid mesh that I want to connect to a shell mesh. So if I, in this one, plot the shell in this specific example, they're exactly the same thickness. So these are shell elements and solid elements.
Just confirm, you're sharing your Teams
Not screen,
link.
okay. I was sharing, but I think it stopped sharing. Okay, so let's try again.
That's good.
Apologies. When I connect the second screen, it messed up. Okay, so the idea in this session is to talk about uh, connecting solids and shells together. So that's my shell mesh and my solid mesh. And in this specific example, some of the others, they will not tie up. In this one, they do tie up. So you can see there's one element in that direction for every shell that there is for a solid. Now, the thing is, this is something that we've wanted to do and needed to do for a long time in finite element analysis. It's the case where we've got some small part of a structure, let's say a joint or something, where using shell element just won't cut it. It's not good enough. We need to model finer or more detail. So in that case, we need to model that part as a solid and then connect to a shell mesh further away at some point where it's not too critical what happens in this region. I just need a really good load transfer and the correct stiffness transfer and so on across that. So some of the earliest methods that's being used would be, if I zoom in there, if we connect that node through some kind of a multi-point constraint to these. Something like an RB2 in Nastran terms, Marc terms the same. It's a rigid connector. Nastran actually has a special element, an RSS con rigid shell to solid connector element. That does the same. The main difference is the RSS con compared to the RB2 is not very stiff in the thickness direction. But the idea behind all of those is to connect the translations of these two nodes to the rotation at that center node. And the translations of those back to the translations at that node for the shell. So by doing that, we can then get both force and moment transfer across this kind of a boundary. Now, the reason we want to do this, we can get really good answers out of a relatively coarse shell model. We often need to model the same part with solids a lot finer, sometimes multiple elements through the thickness and so on. Okay, so if I go to here's some examples. Let's look at the first one. This pretty much is exactly what I've shown you just now. What I connect this node on the shell to these two on the solid, and I do that multiple times. Obviously, quite a bit of work. It's not that hard to create an automated tool, but there's limitations. Now, I'll get to this one in a moment. The complexity comes in with that method. What do we do when we do not have a one-to-one relationship between nodes? Should that node be connected to only those two or to all of them? The right answer is, well, actually to all of them, but then it causes interesting additional issues. But the biggest issue is what happens to these nodes on the solid there, which does not connect to anything on the shell. Okay, so I know today everybody will say just glue it together. Now there's complications with glue, and this is what I'm going to try and explain. So this is one of the oldest methods. This is a method that's available in Marc, so some solvers may have a similar method. This is a hex element, not a penta element as it looks. So if I go back to this model, it's as if I say pick all of these nodes. There to there, and we'll move them down. So move, sorry, nodes by -1 millimeter. There's a 2 millimeter thick plate. So I move them there, I move those up, and then I equivalence the nodes there. Okay, or sweep in Menta terminology, merge in others. So if I look at the element types, go to the types, you'll see this is, according to that, the X8 element. Now, obviously it's not, it is a collapsed element to some extent. However, there's an interesting one that's available in Marc for the thickness or how to connect these two together. So if I go to the geometric properties for the solid elements now, there's actually an option to specify a thickness. It's actually called a transition thickness. What this does is to try and add the right amount of stiffness to this element at that node to represent that thickness that is then transferred to the shell. Okay, so some software may have different methods. This is something available in Marc. It's not available in Nastran as far as I'm aware, at least. Other method that was tried over the years to different levels of success would have been, let's add a shell element over there and at the bottom that's attached to the yellow part, but which ties up with the nose on the solid. And then we merged it. So effectively we're adding a little T-piece over there. And because that has got a moment arm, we can transfer the loads correctly. The downside is we're adding material that doesn't exist. So that changes the stiffness characteristics. If this area isn't too important and that change in stiffness is not too important, it may be a viable method to do. But then what people tend to do today is just to glue stuff together. So this is what I've done for the last 4, but I've used different mesh sizes. Mesh densities, but I on purpose kept the shell element mesh the same. So even this is actually a relatively fine mesh. If I look at the thickness included, if I plot them expanded, that square element represents a volume that's the same, 2 millimeter by 2 by 2 in the thickness. So often we'll use larger elements in these two directions than the thickness of the shell. Okay, so the complication with glued contact comes in with a specific algorithm in use. If I use a node to segment kind of method, in other words, a node makes contact to a face, I want this node to touch that face over there. Okay, so I can do that for all of them, not a big deal. The only thing I have to be careful of is I have to ensure that there is moment transfer across there as well. So if I go to the glue interaction setting, notice there's an option, and it's on by default, to say carry moment for touching shells. It's glue contact, but okay, so I do that for all of them, and I run a node to segment method. Nothing special there. The model runs relatively quickly, but I've already pre-ran it. I think it took 20 seconds or something for this model. Okay, so if I now plot first, one of the first things we always plot for contact is the contact status, to check how it makes contact. If you're not familiar with contact status, it's simply a value that indicates whether or not it's in contact. Value of 0 says not in contact. Value of 1 is touching contact. 1.5 is glued contact for Marc at least. And then there's special values like cyclic symmetry that uses it to thermal near contact 0.5 and so on. So in this case, glued is important, 1.5. Now look at that section, and as expected, the shell element in all of these cases pretty neatly makes contact. Now, this is actually one of the issues, is this doesn't work that well because it's the shell making contact. So the reason for that is this node can touch this face. That solid element, there's no face on this side to touch. If we now look at the deformed shape, let's scale it up a bit to see that may be a bit much. Let's try 5 times. We'll see they deform more or less the same. Not exactly, but at least similar. Okay, so that at least looks reasonable. But if you look at the stresses, I'm going to plot the stress in the x direction, which means I want the tensile stress at the top, compressive at the bottom. Now, if I just go back to show my load cases, there you can see I've applied a shear load, the same for all of them. I've constrained that back node. If I go to the last step again and plot the stress of the top layer, I see something utterly unexpected. It looks like everything is in constant stress. It's not. The only problem is there's these little weird patches that utterly destroys the scale. Now, I know the stress is probably going to be close to about 200. I'll show you now, in any case, 200 up to minus 200. And that's a bit more what we expect. So we see some kind of a tensile at the top and compressive at the bottom. If I, for the shell, want to see the bottom, I have to plot the X component of stress for the bottom layer. So that kind of aligns, that kind of aligns. Now the problem was we've seen insane stresses of the order of gigapascals in that, and even in this model, we see pretty large stresses over there. Now the question is why? Now if you go back to the whole argument about nodes making contact to faces, that node effectively makes contact to that whole face. If I zoom into this one, in theory, that one makes contact to this face. That one makes contact to these two faces. They don't make contact to that section because, well, the mesh is finer. So that finer mesh already messes up pretty much everything in the result. If I go to this section, now this is second order TET elements. So there's further complications. There's a mid node there on that shell, which again isn't connected. We're connecting there to, well, in theory, that edge, but there is a node there, but that's a mid node. And that load transfer is going to be pretty strange for a second order element. I don't know whether you've seen it, but if I apply constant pressure to that face, we actually see really weird forces, some tensile, some compressive, that represents a constant stress state. Now, same happens over there. So again, we've got really high stress in some of these spots, lower stress, but it only attaches at that location to that face, or the close ones, that location to those close ones, and so on. You can see it slightly better if I plot the contact normal forces on these. What I expect to see is a tensile force at the top and compressive at the bottom, as this single element through thickness nicely shown. But once I get to this one, I see already some really strange behavior. So it's tensile there and compressive there and nothing at the top. Even weirder for that second order model. Here you can see different directions for loads and so on. Okay. So obviously not a great way of modeling it. And the reason is mostly because firstly, we're only making contact at separate spot, those faces and these faces, but also we effectively only make contact to that closest section. It's as if there was a crack in this face from there to there and there to there, which causes these really weird stresses. Okay, so what we'd rather do, and I've already alluded to this, is I don't want to make contact from this part to that. I'd rather make contact from there to there, except there's nothing on this side. Okay, so if I switch to a model that I use just to explain what I'm actually interested in, if I create the skin shell mesh over there and I've picked them so that there's a single element, that's not one and one, it's one single element to show that that's one element. And I rigidly connect the corner node to that center one. Then effectively what it says is the motion of that node determines what's happening at those two locations. I then define a very low stiffness for this element. So I'll create some kind of a dummy material. So just to show you, so that is the blue, the dummy material. And the stiffness is insanely low, 1 MPa instead of 200 gigapascals. The same goes for the thickness. I've made this ultra thin because I don't really want these elements to do anything. I just want them to be there to be a convenient spot for the solid to attach to. So the purpose of that blue section is actually to represent that end face of the solid. So if I plot this in 3D, sorry, shells expanded. You'll see that's my thickness that I want to represent, and this is just a little skin there that the solid on that side will be attached to. So I can actually activate them. You can see what it looks like. So this element will be glued to that blue part over there. So the advantage of this is now all of the nodes across the face makes contact against effectively the shell element, that end face, which initially in the shell model didn't appear. Okay, so for this one, let's stop plotting and expand it again. If I run this model, I get a much more interesting result. So let's check contact in this case first. And I'm still using the node to segment. So the nodes of that one is now touching the faces on that shells. So I can plot the contact status. Now that kind of makes decent sense. Now the stress in this section is going to be really low, so I can just as well not plot them. So contact, we can hide those dummy shell elements, which simply represents the end face. Now I can see that the solid element is glued to that as expected. And what's nice is now all of those nodes on that face is attached instead of just here and there a set of nodes making contact. In terms of the result for this one now, I can plot the component 1, 1 of stress. So that's again the X component of stress. And this is now, I didn't change anything on the scale. So the scale, you can see that it's set to whatever the actual default is. So instead of that insanely high stress with really weird stresses over there, it kind of makes sense. Yes, the pattern doesn't make too much sense yet, but again, I didn't bother getting a perfect mesh. But you can see as you mesh finer from a coarse state 10 to a finer one, we start getting better answers. This is a finer but first order X8 mesh. So we already see reasonable answers for these. There we can kind of see that pattern wanting to form, definitely not perfect. Okay, so this is a much better method, but the downside is it's quite painful, as you can imagine. We have to now manually add that. We have to manually create the rigid between them. We have to manually keep track of what makes contact and what not. If I now go back to the regional model, and all that I do is I change from node to segment. What the purpose of segment to segment is, it's face-based contact. So it touches at it picks a series of small points effectively on each face and makes contact. And what it does for shells is that end face there actually has got that same thickness included that we just manually had to add. So just changing to segment in this case, I will rerun it again, it runs relatively quickly. If I look at the contact status now, contour bands of contact status, you should see an interesting thing there. I now see a contact status on both sides because these make contact to that end face of this, and each of these nodes make contact correctly again. So now it's effectively double-sided contact simultaneously. It does make contact to the right face. And what's better is if I plot stresses on the end face, now I need to scale the results. It's again the same default values that I've plotted, and I get very similar answers to this weird manual method that I had to use. Now, just for reference, we'll look at this one from the top, and we'll plot the same 3 of those, looking at it from the top. So those elements, scale them. And if I switch between, this is the segment to segment method where I didn't do anything special, and this is the node to segment, but using that shell elements at the end. You can see if I switch between them, there's very little that changes in these regions, which is really important. That's where we're interested in why we want to model. This is where the solid will be. But there is a little bit of a difference there in these regions. If I switch between them, notice there's more yellow than orange. And if I switch for the other one, there's a bit more orange than yellow. For this one, there's a little bit of yellow there. There's kind of 2 rows of yellow at that location. But if we look at what's happening on the shell side, there's almost no difference. In other words, the load transfer between these 2 methods effectively are both the same. They both give pretty good answers. Okay, so in summary, what we always face when we have these multiple parts together is I have to in some way connect shells to solids, which is a bit of a pain if you don't use glue contact or some equivalent method. There are simpler methods like, and if I go back to this example again, I plot everything. These first 2 models where I approximated it using a certain special element that allows connection between shells and solids, or in this case where I've rigidly connected them, both of these are relatively limited because we can only have one through the thickness. In theory, I can have two through the thickness there and still make it work, but more than that, it won't work to connect from the solid to the shell using rigid connections. In this case, that only allows, and again, we may be able to tweak it a little bit, but ideally probably one through the thickness. If I look at my stress patterns, these are not quite converged yet. I need to mesh finer to get the converged stress, which means effectively, while these are useful, they're definitely not perfect, and I'll rather go for one of these kinds of methods. So once I get there, I'm forced to use either glue or I have to in some way skin that front face and connect them. But in this case, it won't work because I've got fine elements there and pretty coarse elements in this direction. This is all first order, and first order, so I can make it work. For these second orders, I won't be able to create a second order skin there and merge with a first order. Even if it works, I'll get terrible answers. So directly connecting nodes for finer meshes simply does not work. So that means we have to use something like glued contact. If you use glued contact, again, it doesn't make too much sense to go from the coarse mesh on this side glued there. And unfortunately, that's exactly what I want to do. My shell, the coarse mesh, is now connected glued to the solid if I use node to segment or node to face-based contact. If I do the opposite again, if I can glue from that side to the shell, I can have a much finer mesh on the solid side, which is exactly what we need, and still get a good connection between them. And as I've already shown, we can do that manually through a bit of a painful process, but still completely reasonable at least, using node to segments, special skin shell elements, or we can simply use the segment to segment method that automatically does that in any case. And then we can get this kind of results. Okay, so that brings me to the end of what I wanted to show in this discussion on ways to connect shells and solids. If there's any questions, any comments, please let me know.
Hi, Gerrit. This is Deşref. I sent two messages in the chat. Do you happen to have the baseline model for this all hex mesh, just single solid part without any kind of contact, just to check what the baseline original stress distribution looks like?
Okay, so for this one, I didn't build such a model. It's not that difficult to do. But what's interesting is if I look at the shells on this side, all of them look the same. If you want, I can quickly add that as well to show what the result should be.
I mean, it would make sense to check that one with this, so
Yes.
we understand better what the actual distribution should look like.
Yes. Now I understand. But again, that depends, unfortunately, on the software. Nastran's elements tend to be more accurate. So one through the thickness, I may be able to get away with Nastran. With Marc, as you can see there, we still need a bit more elements through the thickness to get a great answer
Yes.
for first
Yes.
order X's.
Yep, like 4 elements in that, I guess, would help. 4 elements through thickness. Something like your third model with 4 elements through thickness, I think they should represent it.
So just say again, but 4 elements. So I talking about one I have or one I should have.
Your third model, I guess, when you check from the one that is closest to you. I mean,
So
is it easy to add a baseline model in here with just like 4 elements through thickness, all hex, first order?
I don't have, as I say, I don't have one, but it's pretty easy to add. For that matter, I could have used shells and extended it. It's still within shell theory. Then I can also see how it behaves.
Yep, yep.
But again, it's easy to add. I mean, that's the purpose here was more to show how to get correct load transfer from shells on this side to solids on that side. Meshing finer, either like this or meshing with only solids, only shells, will show you what the actual stress is.
Mm-hmm. Okay, just to compare these stress distributions with the actual case, that was my point on that. If it's easy to add. Another comment in the chat I wrote is the dummy thickness, what if the dummy thickness is not 1 millimeter, but 1/e minus 5? So it's very, very thin.
Okay.
Have you
So
experienced like singularity on
in
those
theory, it shouldn't
elements?
make a difference. I can quickly do a test and show you. And the reason for that is that why I don't expect it to become an issue is because the stiffness for those elements are actually fully defined by that rigid and connecting to these. So let's just save this test model. So bear in mind my diamond materials are already pretty low stiffness. So if you make it too thin at some point, you may run into issues just getting the contact to happen. But again, that's not that hard to fix. So shell, it's set to 2 millimeters. No, just for the dummy shells, it's already set to 0.1. So let's make it 1e minus 5. Get 1e minus 6 even and see what happens. Okay, so nothing happened. It still worked.
Okay, same stuff.
So the only reason I need to add any properties to it is the solver doesn't like elements without properties. So I just need to ensure that the stiffness is super low for that, because the stiffness comes from the shell elements, not from the solid. But again, this is not something I'd recommend. I'd much rather use the segment-to-segment method, which if I look at that front section, I see is not that great. I expect to see that the segment-to-segment will most likely have a slightly better distribution there at the front. Now again, it can't be perfect because we've got really large elements there, but let's see what it looks like. Yeah, if I look at that through thickness trace there, that actually looks pretty decent. So at the top, there's a little bit of variation, but through the thickness is nice and linear. This one through the thickness is okay, not perfect. Let's just hide these dummy elements. Yeah, so to be honest, this actually looks okay as well. Not great, but much better than any of the alternatives. Yeah. Any other questions?
Just to confirm, your choice is this one, right? Among all the 6 models, this is the best you like.
In terms of results?
Yeah.
To be honest, this isn't about results. This is about which method to use. My preference would be for using normal glued contact, but segment to segment. And then by all means, you can mesh finer and use different meshing strategies to improve the mesh. This session wasn't about getting the perfect answer there. It was about seeing what the effect is of how I connect shells to solids. So I'll still rather probably go for first order X's, mesh it finer, and probably at that interface maybe mesh it a bit finer, although that's not too important for this model. If it was Nastran, I think TET or X would have been fine. Both should actually give good answers, even for 3 through thickness.
Yeah, just the mesh in the third and the fourth models, the stress on them look different. The third and the fourth models.
So that one and that one.
Yes.
Yeah, obviously this is 4 through the thickness, that's 1 through the thickness.
Mm-hmm.
So it's one of the big issues we have with this kind of a model. We expect to see a constant stress in that direction, right? So the stress in the X direction, but we expect to see the same stress there and there. Do you agree?
Mm-hmm.
The reason we don't is because of Poisson's ratio. So as I load it down, there's a tensile stress at the top, which means due to Poisson, it shrinks at the top in this direction. At the bottom, it compresses, but it expands. And that caused that section to actually form some kind of a bow section. So let's rerun this one. Just save it also as another test. And we change the material Poisson's ratio to 0. So then we don't have that secondary effect. So then I expect to see a cleaner distribution. There will be a stress concentration at the back, but over there, arguments like I expect to see the same stress there as there. Yeah. Now we have a near constant stress in that direction. And just at the back, there's a bit of a variation. I changed the numbers a bit, so that has got that kind of a pattern. The stress is lower because the element is less accurate, and for the mesh density we've used, so let's try minus 200 up to 200. Yeah, we still see a bit of that pattern. We need to look a bit further, so let's try 180 to 180. Yeah, still unfortunately not that clear. We need to get further ahead. Then we start getting close to that kind of a pattern. But again, it's if I look in that direction, that's a lot more elements than from there to there. So it doesn't have enough distance yet to fully recover from those stress concentration in this case.
Okay, thanks.
Any other questions? Any comments?
Thanks,
Okay,
guys.
so
Appreciate it.
yeah, thanks. So if there's no further questions, thank you for joining, and have a good rest of your day.